Okay, so ladies and gentlemen, today we're going to be going through a set of final materials, just wrapping up our discussion of infectious disease models and nonlinearity. We're then going to transition to a discussion of agent-based modelings and introducing some basics of agent-based models. So this wrap-up for infectious disease models is one that I don't expect to take more than about 20 minutes, but it'll provide a certain, hopefully, closure on a few issues. You recall that a defining characteristic of these models has to do with the transmission of infection from one person to another, going from susceptible to infections to infective individuals. We have a term that's termed the force of infection that represents C times I over N times beta. So again, what is C here? What's C? Contacts per unit time, okay. What does I over N represent? Yeah, the fraction of the population that is infectious, or the part of the population that has your product or what have you. And beta here is the what? It's a probability, yeah, of transmission. That's right. Now, you may recall that we can rewrite this term in this sort of way. S times C times I over N times beta. So actually, this is for the whole flow. The whole flow has that force of infection. If we wrote it here, this is the force of infection, and the entire flow is just S times that force of infection. The force of infection is a hazard rate, a chance per unit time of getting infected per susceptible. So the number of people getting infected is S times that per unit time. So if it's 1% chance per day, and we have 100 people at risk, or say 1,000 people at risk, and it's 1% chance per day, chance of each of them getting infected. On average, how many people per day will get infected? 1,000 people at risk, and 1% chance per day. On average, how many people per day will initially get infected? 10, yeah. 1,000 times 0.01, right? So we can represent the flow using this sort of reasoning. Another way to rewrite it, though, would be this way. I times C times S over N times beta. We talked about this last time, in fact. I here is the total number of infectives. This is taking it from sort of the perspective of an infective. Each such infective infects this many people, C times S over N times beta people per unit time. So that's the number of people on average that they infect per unit time. So they're surrounded by, where they encounter C people per day, 100 people per day. Of them, say half are susceptible, 50 people per day are susceptible, and each of those people, they have a chance of 0.01 of infecting, something like that. So on average, they infect 0.5 per day. Or each of them, they have a 10% chance of infecting, beta equals 10, in which case 50 people per day, or 100 people per day, 50 of them susceptible per day, 5 per day that they infect on average. And we termed this S over N F because it was so critical. And when we looked at interpreting the dynamics of the infection, we found that F was critical. It was critical because it limited the spread of infection. If you're an infective and you're surrounded by susceptibles, you're gonna transmit much more effectively, much more efficiently than if you're surrounded by very few people who are susceptible. Or if you're a new purchaser of an iPhone, a new model of iPhone, you'll influence more people if you're surrounded by people who are not yet owners of that model and are interested in it, rather than people who already have it, or who have moved moved to other products and are not interested in it anymore, recovered, so to speak. So this fraction F, it turns out to be critical. It's a critical limiter on the spread of infection. And I argued here that over time, people spread infection in ways that are progressively less efficient as the number of susceptible individuals, or the fraction of susceptible individuals in the population, goes down. And we computed this quantity, R star, which is called the effective reproductive number, which basically tells us how many people a given infective will be infecting right now. Now, I'm trying to find if I had that that formula. It doesn't look like I have it on the slide, so I'll put it up here on the board. R star here, the number of people infected by a given infective before they recover. Right now, we'll call R star, whatever situation we're in. And typically, in a model that's as simple as we've been looking at, it will be C times S over N, we can call this F, times beta times what? What's missing here? What's missing? This is a total number of people that they'll recover before they recover themselves. They'll infect before they recover, R star. So if I write this, C times S over N times beta, does that have the right units to be number of people? No.
Multiply by time?
Yeah, we have to multiply by time, the duration infected. I'll call it D. Often we've written it as mu, sometimes as tau. Whatever you call it, this is the duration of infection, okay? This is the number of people that infect per unit time. Remember I said just a few minutes ago here, I said that this is the number of people, C times F times beta is the number of people they infect per unit time. So if we want to find out the total number they infect, it's that times D, the duration of infection. Yeah. Duration of infection. Duration of infection. Okay. Now this is R star. This is the number of people they'll infect before they recover. And what was the key threshold for this? At what threshold would the disease be in balance? No longer rising, no longer falling. If R star equals what? Okay, it could be depending on what I star is here, but I'd like to guess. So at what point will I no longer be contributing to a rise in population of the number of infectives? Suppose I am an infective. I become infective, and before I recover, I infect 2 infectives. Have I contributed to a net increase in the population of infectives? Yes. Suppose when I become infective, before I recover, I on average infect 0.5 infectives. Have I contributed to a net increase? No. So what's the key threshold? This equals 1. I replace myself. I infect one person to replace myself. At that point, the infection is not rising, it's not falling. This is the situation, ladies and gentlemen. That is the situation. R star equals 1 is the situation where the system will be in balance, okay? It'll be in balance. It will no longer be rising and no longer be falling, okay? It'll be a situation where if you have an open population, a population where we have, and I wish I had a good picture of it here. Yes, here, right here. We have a situation where the number of infectives is no longer rising nor falling. It's flat. We could say at the high level, at the level of the aggregate perspective, what is the case for infectives? The stock of infectives, what must be the case for the stock to no longer going up or down? What must equal what? Inflow equal outflow. Alternatively, at the level of a particular person, what is the case is each infective infects how many people before they recover? 1. That is the situation of equilibrium, ladies and gentlemen. That's the situation at which the system's at rest, no longer rising and no longer falling. And you'll notice that it's at that point, in terms of the number of the fraction of susceptibles here, that it's at that point where it's equal to that key threshold, where you'll in fact have the key points noted below. So for example, it's when susceptibles cross going upwards, that threshold here, just the blue curve, the fraction of, indicating the number of susceptibles, and hence the fraction directly, since it's a fixed population. It's at that value of susceptibles that the number of infectives starts to rise. It becomes efficient again to spread infection once the number of susceptibles goes above that. When the number of susceptibles goes below that, like here, the number of infectives will start to do what? So here, the number of susceptibles is going up, and therefore it crosses this key threshold where it becomes worth it to be an infective. Worth it because they can spread to more than one person. Does that make sense? They're spreading out to more than one person. By contrast, here, the number of infectives is the number of susceptibles is going down below that threshold, and it's no longer worth it to be an infective in the sense that you infect fewer than one person before you recover. You don't even replace yourself. So when it goes below this point, the number of infectives starts to go down because they're not even replacing themselves. When it crosses above this threshold right here, I'm looking at this vertical threshold as indicated by equilibrium. When it crosses above that there, the number of infectives starts to go up here. You'll notice that it's at those points that the system is sort of turning around its focus. You'll notice the same thing occurs here. Right at this point, at its equilibrium value in terms of the number of susceptibles, the number of infectives is turned from going up to going down. Because it's at that point, ladies and gentlemen, that R star equals 1, that the number of infectives is in balance. If R star is less than 1, the number of infectives is going down. If R star is greater than 1, it's going up. And the key thing that limits R star, the only thing that's changing over time in this whole formula, C times S over N times beta times D, is what? What's the only thing changing here? It's this, S, and by extension, S over N. I mean, as a quantity is changing. The fraction of susceptibles that are infected. Here, the number of susceptibles determines it entirely. So, ladies and gentlemen, the number of susceptibles becomes the key limiting factor, okay? It's the key limiting factor for whether we achieve an infection that's rising or falling. If we can lower the number of susceptibles, then we can take a situation out of a situation where the infection spreads to where it's declining. Now, what's one way? If we think about your experience with flu or your experience with chickenpox and measles and etc. when you were very young, perhaps, what's one way that we decrease the number of susceptibles in a population? What do? We vaccinate them. That takes them out of the susceptible stock and puts them into the infectious stock. Okay? So, puts them into the recovery stock, the stock from which they cannot get infected. So here, with vaccination, we are trying to lower S over N. We're trying to lower it dramatically so that it won't spread. Now, I want to make the analogy here with R star to a very special situation, which goes by the name R naught, R0. Okay. R0 is R star in a very particular situation. R0 or R naught we're asking about R star in a very particular situation where everyone or no one is infected right now. Everyone is surrounded by susceptibles. So it's the worst possible situation if you're an infected in terms of, well, it's the worst possible situation for the population. It's the best in terms of infecting people. If you're infected, you'll be highly efficient in spreading it. Okay, so ladies and gentlemen, if we have R star, that's the same as, sorry, if we have R non, R sub 0, it's the same as R star. I wrote it with a superscript star. I'll write it with a subscript for consistency here. It's the same as this for the case where S equals N. Everyone is susceptible. So what will R star be for a model like we've been examining? Can anyone, sorry, R0, what will it be? If S is equal to N, what is R star going to be for our model? What's the formula for it? I gave you the formula for R star, and I told you R0, R naught, is equal to R star for the very particular case where S equals N. So what's the formula for this? C times beta times D. That's R0. R0, the intuitive meaning of it, is the number of people that I would infect as an infective if I come into this population and everyone around me is susceptible. How many people do I infect? How many people do I infect? For measles, it's about 16. If you come into a population and everyone around you is susceptible to measles, you'll infect about 16 people in many social contexts. In other social contexts where you have fewer contacts, you might infect somewhat fewer people. But these are highly transmissible infections. So much of what we try to do with vaccination is bring it down to the fact that even if everyone else in the population is susceptible, ladies and gentlemen, everyone else in the population is not vaccinated is susceptible, the infection still won't spread. And that allows us to achieve what's called herd immunity. The infection, the population as a whole, there are still people in it who are or maybe subject to infection, but we have enough people who are vaccinated that we will not see the spread of infection in the population as a whole. Okay, so here R0 is just the contacts per day times the per contact risk of infection. So this is C times beta times D. Okay, that's the total number of people infected over the course of infection by an index infective who comes into a susceptible population. Now, if we want to figure out what this is, okay, what we need for the infection to die out here, we need a fraction of people who are immunized, who are vaccinated, such that we get a situation where F times R0 equals 1. So you'll notice this S over N, we call it F, okay? And I would argue R star, in general, R star is just equal to R0 times F, okay? So it's R0, C times beta times D times F here. See that? It's R0 times F. This is R0 here. I'll rearrange the terms if it would be simpler. There's R0, and here's F. F times R0. F times R0. Right there. Okay, so R star is just equal to F times R0. Under what conditions, ladies and gentlemen, will we have an outbreak occur? Under what conditions will infections start to spread, to grow larger, the number of infectives in the population? We told you earlier, if R star is what? Greater than 1. Okay. R star greater than 1 implies that it will spread. If R star is less, so here it spreads. If R star is less than 1, it will decrease, right? And R star equals 1 is just at the threshold, so infection decreases. It won't catch in the population. R star equals 1 is that key threshold, okay, where it's in balance. Let's consider a situation where we want to achieve infection decreases, okay? What we need, if we need R star to be less than 1, if that's our goal, that we want, no matter, even if someone comes into our population, we want a fraction of susceptibles that's small enough that R star is less than 1, then substituting this in, R star is just equal to R0 times F is less than 1. What do we need F to be? What do we need F to be here? If we want to achieve a situation where we're handed a given disease, it has a given R naught, it has a given duration of infection, we're given a certain contact pattern, and we're given beta, the chance of transmission from a susceptible to, from an infective to a susceptible. Then we need F. If we want R0 times F to be less than 1, that's just what this is, F times R0. I'll write it even in that order. F times R0 is less than 1. Then what does F need to be? Less than 1. What is it? Less than 1 over R0. Right? So we need the fraction of people who are susceptible to be less than this. If we achieve that, someone could come in with infection and they could land in the South Sudan airport, and we as a society don't have to worry about it. There are still susceptibles around. The fraction that are susceptible is just small enough that it doesn't stick, because F is less than 1 over R0. How did I get this again? I noted that, look, R star is equal to C times beta times D times S over N. Where did those come from? Well, from simple reasoning about the situation. Each infective, in fact, it contacts C people per unit time. C times S over N is the number of those people per unit time they encounter that are susceptible, times beta, the chance of transmitting to each susceptible. So C times S over N times beta is the number of people to whom on average they transmit per day, times D is the length of time they're infected. That's on average the number of people they're infecting right now. And I argued that R0 is R star for the very specific case where S equals M. And therefore, it follows that if we call S over N F, that R star is just R0 times F. And we noted that the disease will die down if R star is less than 1. If R star is just F times R0, the fraction that are susceptible times R0, then F times R0 is less than 1 implies F is less than 1 over R0. And if this is the condition for the infection not to stick, that it will die out if it's introduced. This, ladies and gentlemen, is what we try to achieve through vaccination. We try to have few enough people that are susceptible that no more than 1 over R0, a fraction of them are susceptible. So we need to immunize the rest of the population. We want to immunize. So this implies we want to immunize the rest of the population, okay? If F is the fraction that are susceptible, and we achieve this, we have to immunize, so in other words, vaccinate at least what fraction of the population? At least 1 minus this. This is the fraction that are susceptible. We're going to immunize everyone else. So at least 1 minus 1 over R0. So consider measles. 1 over R, if R0 is about 16, 1 over R0 is about 6%. So you need to immunize about 94% of the people out there to avoid a measles outbreak. You have to immunize enough people out there that about 94% of the people are immune to measles. If R0 is 10, you need to immunize what fraction of the population? If R0 is 10, the fraction you need the fraction of susceptibles to be less than 1. If R0 is 10, you need the fraction of susceptibles to be less than 10%, which implies we need what fraction vaccinated? 90% of the population vaccinated. Now, this notion of herd immunity is a emergent notion. It's a collective notion. It's not a notion of a particular individual. Are there people, suppose we vaccinate 95% of the population for a disease whose R0 is 10. Are there people out there in that population who are susceptible? Yeah, there are. There are people there who are susceptible, sure. It's just there are enough people who aren't susceptible, 95%. The disease won't stick. It will infect a few people perhaps, but it won't be able to spread efficiently because it's really inefficient to spread because each infective is surrounded by people who they can't spread it to. It would be like having fire land in a field that's quite wet. You might spread to a few branches, a few twigs, a few pieces of grass, but it's not going to spread across the whole because it's just not susceptible enough. It's not dry enough. Okay, so ladies and gentlemen, this criteria with the fraction that are susceptible is the key to today's vaccination programs. This is what they shoot for. This is the reasoning based on it. They want to get that. Now, as we'll see, starting today, a new form of modeling we'll be using, agent-based modeling, will actually help us sharpen this more. Here we're dealing with generalizations of the whole population, but in fact, people who are not vaccinated tend to cluster. So you may have small pockets where the disease can spread, and then other pockets where it doesn't. Or we may have small pockets where contacts are higher. Some of those pockets might be called children. And for those people, there might be a greater risk of the infection staying present when it would otherwise disappear. But this general notion of achieving herd immunity and achieving a fraction of susceptibles less than 1 over R0, this is the foundation of a lot of theorizing on modern vaccination. That's sort of the basic idea that we're trying to achieve. And it comes out of these basic concepts. So this R star, this is called the effective reproductive number, and R0 is called the basic reproductive number, okay? R0 is just R star in a very particular case. In what case? R0 is R star in the case of what? In the case where S equals N. In other words, yeah, if everyone is susceptible, how many people do you infect? Okay, before you go. You'll see this sometimes in the popular literature too. They talk about the R0 of Ebola. They'll talk about R0 of some new thing that was discussed. They often won't use that term. They'll just say it's estimated that each infective infects a certain number of people before they recover or die, and that's R0. Okay, so that was one little sort of wrap up related to infectious diseases before we leave this topic. There's one other topic though that I wanted to hit on, and that had to do with the notion of non-linearity in the context of these models. And I had it up here, and I'm wondering where it went. So pardon me for just a second here. Okay, now I'm in trouble. Mimic modeling. Okay, I think I know where it is. Okay, let's try this. Oh, okay. Pardon me for a second, folks. Here we go. And we had set of demonstrations, but here we are, right here. Excellent. Okay, so let's get this show on the road. Boom. Okay, so folks, why is this model nonlinear? I wanted to show it to you. I've claimed this model is nonlinear, and I waved my hands and I said it had something to do with these equations here, the flow out of susceptibles, the flow into infectives. In other words, the infection flow within these models, this flow right here. I said it had something to do with the fact that it S times I, but I didn't really explain it. But it has the multiplication of two-state variables. That's the key thing. We're multiplying this times this. And I want to give a brief explanation to why this is nonlinear, okay? And I'm going to give, in fact, two explanations from different angles. One thing is, look, we have a linear system. We have a system that's linear. We can write x dot equals f of x. In a way that uses purely linear transformations of x. So specifically, we can write x dot equals some vector plus some matrix A times x, where this is matrix multiplication, the times sign. In other words, all this matrix does is it takes linear combinations. So it takes 0.2 times the first element of x plus 0.3 times the second plus 0.1 times the third. That's what this is. This A is a vector. It's a vector of constants and vectors. It's a matrix of constants. So when applied to a vector, all it does is have a linear transformation. And it combines the elements of the vector in a linear way. The first times some number, the second plus the second times some number, plus the third times the number. It takes a dot product, as it were, of the rows of A with x as a vector. To determine each successive element of the product here. Now, turns out we can rewrite this through a simple change of variables for anyone who's interested as x dot equals capital A, that's the same matrix, times x, okay? It turns out that given a system like this, it can be directly rewritten like this. And this is a linear system. What it's saying is the rate of change is just proportional to, using this matrix, it's proportional to the current state. So if we double the current state, the rate of change doubles. If we double x, for example, we'll double the rate of change. Why? Because x will be twice as big, and we can take the 2 out in front, and the rate of change will be twice as big as it was with the original value of x. Let's take a look at this further, though. So this is one situation we have. Now, in our case, this is what we have. In our case, we have x dot, that's here, si and r with a dot over it. And here, we could write this, the system like this. This is just the same system we've been dealing with. This is the same equations right here. I just rewrote this in a matrix form. This is a matrix way of writing it. SIR is on the left-hand side, just hewing to this sort of way of writing it. It's x dot, that's what this is. SIR is x, the current state of the system, plus it'll be an A plus these things here. So the A is just M00, and then it's a matrix times SIR, okay? And I wrote it like this. So I should actually be careful here because there's actually this needs to be over on that side as well. So here, this should be like this. Boom. Now these things will be a bit off, but there we go. Okay. So here we have a situation where we have m. So we can re-express this as m, a vector of m. Where did I get that vector from? It's just this constant. There's no constant term in the second element of this vector up top. No constant element there, 0. So it's 0 for those plus these and m at the top. And then this is the way of rewriting these terms up here, in matrix form. So where does this c minus c times I over n times beta come from? Where does that come from? Which term up here? Sorry? Yeah, it's this one here. Why isn't there an S down here? Because it's multiplied by S. That's what happens, right? If you have a matrix, take the matrix product of a matrix on a vector, the matrix operates on the vector. That's what matrices do. They're operators. You apply them to a vector and you get out a what? When I apply a matrix to a vector, I get out a what, folks? A vector. I apply it to the vector and I get a vector. It does something like transform it, it rotates it, and stretches it, and so on. Collapses it in a certain way. So here, I can rewrite these top terms up here using this simple notation, this matrix notation. This times S, and it's a minus sign here, and nothing times I, and nothing times R. And then I have here C times I over N times beta times S on this row. And then I have minus 1 over mu times I and 0 times R. And then down here in the lowest row, I only have the term times I. And so I have 1 over mu in the lowest row down at the bottom here. Okay. So I've rewritten this in this matrix form. The thing is, ladies and gentlemen, this is not a linear system. And it's shown by the fact that these entries in the matrix are not what? They're not constants. They depend on the state, the number of people infected right now. So these are not constants, and therefore it does not fit the need of a linear system. If we had a linear system, A would be composed only of constants. We don't have a linear system here. A cannot be described only in terms of constants. In short, the rate of change as multiplied by the current state is, or the sort of the current behavior of the system when multiplied by the current state itself depends on the state. So how quickly people are getting infected depends on the state, how many infectives there are. Okay, so this is one sign that it's not linear. We can't nicely decompose it into a vector plus some matrix of constants times x. It doesn't fit that way. We don't have a fixed A that applies everywhere. Or another way to put it is A changes depending on what the value of x is, depending on what the value of I is. So that's one way to understand it as nonlinear. We can't describe it this way with a matrix of constants. Does that make sense? Okay. A second way to demonstrate this is, look, with a linear system, for any nonlinear system, f of a plus b is equal to f of a plus f of b. This is the most delightful thing about linearity. If we're dealing with a linear system and we're dealing with some complex god-awful input, we can take it apart into its constituent pieces and reason about the behavior of the system with respect to each piece, and then just sum that up to get the responsive system to the complex, messy, god-awful input. So if we have this input a plus b, we can write the response to the system, f of a plus b, as just f of a plus f of b. That's a notion of linearity here. Okay. So here, if we have a linear system, x dot equals f of x, if that's linear, then if we consider, okay, how does the system respond to a sum of a sort of a superposition, a sum of two state vectors, x and y, the rate of change, if we consider x plus y, it should just be f applied to x plus y, which should equal f of x plus f of y if this is linear. So suppose that we're considering a current state of the system, Si and R. We have 1,000 people susceptible, or say 999 people susceptible, 1 person infected, 0 people recovered. I would argue that if this is linear, we should be able to divide that up into 2 scenarios that will sum together the response. One, where we have 999 susceptible, 0 infectives, and 0 recoveries. and the other where we have zero susceptibles, 1 infective, and 0 recovereds. And we should be able to simulate each of those, and we should get back a sum of those responses that are equal to the result of what would be the result of simulating 999, 1, and 0. Is that the case? If we have a situation where we have 1 infective, 999 susceptible, 0 recovers, can we simulate the result of that by just considering instead 2 neat little scenarios, one where we have everyone susceptible only, no one else in any other state, and the other one where we have only 1 person infective, no one else in the system? No, we can't. It's totally different. It's totally different. Why? Because infectives infect susceptibles. You can't separate them out. You can't separate them out neatly into 2 separate scenarios where you have only susceptibles on the one and only infectives in the other. It's missing the point, right? The whole is greater than the sum of the parts here. It's missing the point that the system is not just the pieces, the susceptibles in isolation, the infectives in isolation. It's the combination of them together that dictate the dynamics. So this system, by this criteria, fails the linearity test as well. It's not the case that it will meet this nice criteria or this nice criteria. You'll notice here we are describing this as the system over time as a function of its state, of what it takes as an argument. That's how we describe the system. And so we're dealing with, we're trying to deal with the situation of, do we have a case where we can have, this is f of a, or sorry, this is f of a and f of b, and the results of simulating this and summing them together are totally different than the results of simulating the combined system where we have susceptibles and infectives together. Does that make sense? So with a linear system, we could take it apart into its pieces, simulate each in isolation, sum the results together, and get something equal to the results of simulating both together. That's not the case here. This system is not linear, ladies and gentlemen. And it's not linear because of this term. Because here we have this mixing between susceptibles and infectives. We can't consider each one in isolation. We have to consider them together. We have to consider them in a combined way. And one way to say it is the rate of change, the chance each susceptible will get infected per unit time is not independent of state. If I'm in a situation and there's no infectives and I'm a susceptible, my chance of getting infected is very different from if I'm the only susceptible and there's 999 infectives. That's very different chance per unit time of getting infected. The force of infection, C times I over N times beta, is very different depending on that applies to me as susceptible. That's one way to see it. Another way is we can't decompose any state into 2 alternative scenarios, considering each half the side of the state, and then sum up the results of simulating them. So this, ladies and gentlemen, are footprints. These are claw marks of nonlinearity. We can't take the system into its pieces, just reason neatly about those pieces and sum up the results or take the average of the results as we can for a linear system. We can't simply consider each aspect of the situation in isolation and sum up the results. It doesn't work that way. We can't consider it as having a rate of change applied for each person that's independent of all other people in the system. It doesn't work that way. Okay? So this, ladies and gentlemen, is a nonlinear system, and it's nonlinear because of those components. Any question on that? Okay, so what I'm going to do now is I'm going to make perhaps the biggest transition in the course. Okay, this transition will mark the transition between 2 very different types of dynamic modeling. I'll be posting this in my slides, these equations. We're going to transition now from one type of modeling to another with big differences between them. They're going to share certain similarities. Both these traditions And I should really stop this and start a new recording here, because we're recording something which is rather different. So I'm going to stop this, and I'm going to go over here and complete